Okay, good morning, good afternoon, and good evening, everyone. Welcome back. I just wanted to remind you what was going on because you know, at some point I guess you may have forgotten what is going on. So we are still proving that OCAT implies that all automorphisms of the Calkin algebra are inner, even though what we are doing lately didn't seem to have much to do with that. So let me just give you basically sort of a heads up of where we are and what is the plan, so that you can put the material of today's class in context of that proof. So okay, proof of course starts by fixing phi, which is an automorphism of the Calkin algebra. Now here is how roughly proof proceeds. So we prove that for every E in part N, the restriction of phi to f of E. Now, this is somewhat inaccurate. F of E is not even subalgebra. It is a subspace of B of H. So what I should really be writing is the quotient, the image of F of E under quotient map. So phi restricted to P of F of E is, oops, sorry. By the way, right now I am balancing in a very little room my iPad, my laptop, a cup of hot tea, and a bottle of water, plus some hand sanitizer. So I'm hoping that this will not lead to a disaster, but let's hope we survive for 90 minutes. So phi is implemented by unitary. Let's denote it U sub E. Now, for different E's, we have different unitaries, but what we have is a coherent family of unitaries. And we already proved before that OCAT implies that this family E comma U sub E can be, okay, I'll put it under quotation marks, can be uniformized by a single unitary. All right, so basically this is the part of proof that we did, and this is really the long part of the proof. So let me say something that I still find curious, if not annoying. You see, for part 2, we know that this is independent from ZFC, because under continuum hypothesis, we constructed a non-trivial coherent family of unitaries, which gave rise to an outer automorphism of Calkin algebra. And the proofs were reasonably straightforward. For part 1, we'll be using OCA here as well. But two things, a proof is much more complicated than the proof of 2. And second, we don't know whether OCA is necessary. So for all I know, part 1 can be done in ZFC. Just, you know, it's sufficiently complex so that we don't really have a good idea of what is going on. Now, where does today's class sit into all this? Well, somewhere in part 1. So essentially what we'll be doing is the following. Let me, oh, why did I press there? Nobody knows. Let me just add one page. So today, we'll be analyzing D of E. So remember, D of E is those block matrix operators, and we'll be trying to connect D of E to to some descriptive set theory to be used later on in the proof. And I'm emphasizing this because it's probably not going to be quite clear what that has to do with Calculon algebra. But anyway, so that said, I have my chat window open. If you have any questions, let me know. In the meantime, we'll just have to finish what we started last time. Remember, what we had was a sequence of finite sets, dn for n in n. And for x subset of n, we define d sub x to be product of those dn's that whose index belongs to x. Now this is a compact metric space, so here is the natural Cantor space metric. And we describe basic open sets. What does basic open set look like? Well, you fix a finite set of coordinates, and on those coordinates you say exactly what your element is. So they look like little cylinders. Now, before we go on and wrap up what we started last time, let me just say two things. First thing is, you see, dx, the way it's defined here, is a quotient space of dn, right? Because if you look at dn and dx, x is subset of n, you just send a to a restricted to x, right, with the obvious notation, right? We're just taking those coordinates in x, and the dx is a quotient space. However, we'll really be thinking of dx as a subspace of d. So, let me just say how. We'll also, actually, I should say also think, because we have to think of it as quotient space willy-nilly. So we'll also think of the x as a subspace of the n as follows. Assume that each dn has some distinguished element that I'm going to denote 0. And it's actually going to be 0, really. You'll see later on, it will be 0. And so identify some a in the x with a tilde, such that, okay, I'll leave a room here, a tilde of n is a of n if n is in x, and a tilde of n is just that distinguished element 0. If, oops, right, so this is problem with computers. They tell you not what you want them to do, but what you tell them to do for n not in x. Right, so you just pad up with zeros, the missing elements. Now, this is something of abuse of notation. It is the same 0, but it is the same 0 really. So nothing to worry about. Anyway, this comes from the last class, and we proved this basic simple lemma about relation between these basic open sets. Here it's just to remind you what's going on. And here's a theorem that we proved, right? It was in the last moments of the last class, but there is a detailed proof in the book, or you can ask me or Said if you have some questions. Basically, this is a very useful theorem. Set theorists love it in all sorts of different forms. It gives you a very combinatorial description of what it means to be co-meager in a product space like this one. The proof used very heavily the assumption that all the dn's have finite spaces, that's a necessary assumption. Without that assumption, the theorem is just miserably false. So anyway, so basically, every relatively co-meager, remember, co-meager means that its complement has first category. It's union of countable many lower dense sets. Set is relatively co-meager if and only if you can choose countably many of these basic open sets whose support intervals are disjoint. And that's exactly why we wanted support intervals to be arbitrary and not just initial segments of natural numbers, which would be natural choice in pretty much any other situation. So we have these countably many basic open sets, and an element of Dn belongs to your set if and only if for infinitely many of those basic open sets it respects what those sets tell it. Okay, so this was done last time. Now, today we'll do some little bit of descriptive set theory with no proofs. I'm just assume that you either are prepared to take it for granted or that you already know it. And so here is a classical result from descriptive set theory. As you can see, one of the names associated to it is of a set theorist, gone operator algebraist, gone economist, gone game theorist, gone computer scientist, John von Neumann, right, the man of the 20th century. And this was just sort of a trivia. The reason why von Neumann needed this theorem was disintegration theory for von Neumann algebras, which, I mean, he called them rings of operators, of course. So this is exactly a lemma that you need at some point to choose an element which works for something. Now, if you read the statement, if X and Y are Polish spaces, right, separable, completely metrizable, then every analytic subset of the product can be uniformized by a C-measurable function. Now, the way I stated here is probably totally useless, because if you already know what analytic and uniformized and C-measurable means, you probably know this theorem. And if you haven't seen this theorem, then you probably don't know what's C-measurable, at least, maybe even if you know what's analytic or uniformized. So I should tell you what are the characters in this theorem. So what does it mean to be analytic? There are few, I mean, it's one of those notions that has many equivalent formulations, but one general enough for us, it means it is the image of a Borel subset of a Polish space by a Borel measurable function. Right, so you have a Polish space, you have a Borel subset of it. There is a Borel measurable function from that Polish space into your Polish space, which is X cross Y here, and A is the image of that. Now, a Borel measurable just means that pre-image of every open set is Borel, right? It's measurable with respect to a sigma algebra of Borel sets. I mean, I could have, instead of a Borel subset, I could have just scrapped it, just the image of a Polish space by a continuous function. You get equivalent notion, and there are many others. Most useful ones involving trees in one way or the other, but that doesn't matter. Now, second notion that I need to describe, uniformized. I'll just draw a picture here. So here is X, here is Y, here is our set A, so A is subset of X cross Y. Now, what does uniformize mean? Well, it means that the graph of the function is, so this here is the graph of this function, and it is included in set A. Right, so we think of a function as a set of ordered pairs. So there is a function which uniformizes this set and which is C-measurable. And that brings us to the last part of, last bit of something that I need to explain. Sometimes logicians love to call this sigma of sigma 1, 1 measurable. But it basically means Well, it means the same thing. So what does C measurable mean? It means measurable with respect to the sigma algebra which is generated by analytic sets. So it is a classical result of Suslin that not all analytic sets are Borel. There is an amusing story about that famous mistake by Lebesgue, who wrote in his famous thesis that obviously continuous image of a Borel set is Borel. And then you see, this is a good story because it tells you that you should be, even if somebody very respectable says that something is obvious, you should not believe them, you should check it. So Suslin checked it, and he noticed that it was not only just not obvious, but false. And basically started descriptive set theory. Anyway, so sigma, so C measurable is more general than Borel measurable. Now, I'm not going to prove this theorem. You can look it up in Kekris's book, for example, or pretty much any book on descriptive set theory. Now, one fact that we'll need, actually two facts. So, oh yes, actually, as I'm stating this fact, I'll have to introduce more definitions. So let me just finish sentence and then I'll tell you what are other definitions. So analytic sets are bare measurable. Now, you know, everything is happening in Polish spaces. So my ambient in sub-Polish space. Now, what does bare measurable mean? It means that there is an open set such that the symmetric difference between your set and that open set is meager, is of first category. So it's those sets that are modulo first category equal to an open set, i.e. equal to an open set modulo meager. Okay, now since the meager sets form sigma ideal, right? You know, countably many sets, meager sets is by definition meager. What this fact implies immediately is that C measurable implies bare measurable. Namely, every C measurable function is also measurable with respect to a sigma algebra generated by open sets and meager sets, which is strictly bigger than Borel sets. And this is what we need. Oh yeah, there is one more fact that I'm going to need now that I'm talking about, and this is really, anyway, this is also an easy fact. So if X, Y are Polish and F maps X to Y is bare measurable, then there exists some set, let's call it G, subset of X, which is dense G delta, and such that F restricted to G is continuous. Now, you don't really need both spaces to be Polish. It suffices to have Y second countable and X bare, but let's say X is Polish. So basically proof of this is so short that I can just tell you what it is in case you haven't seen it. Basically, since Y has countable bases, just enumerate some bases for Y. And now a preimage of each one of those basic open sets is bare measurable. So there is an open set equal to its that preimage, which means that once you remove meager set, that preimage of that open set is open on the complement of that meager set. So you just do that for each one of those countably many basic open sets. You remove countably many meager sets. What remains includes a dense G delta set, and the restriction of function on that set has the property that preimage of every open set is open, therefore it's continuous. Right, so we'll be using this. And here is a corollary that I said I wanted to do last time, but maybe it's better that I didn't rush. So here, let me just add a page. Oops, this was not how you add a page. Right. So if Y is a second countable space, and Fn mapping Dn to Y, so Dn is, as before, this product of finite spaces, so you have countably many bare measurable functions, then there are infinite X subset of N, and element B in D sub N minus X, such that the function Gn from dx to y defined by Gn of A is Fn of A plus B. I probably owe explanation of what is A plus B. It's really a concatenation of A and B. So A plus B of N is equal to A of N if N is in X, and it is B of N if N is not in X. Right, so this function, each one of these functions is continuous for all N in N. We'll use this later on in the proof, so let's just sketch a proof. Well, first, each Fn is continuous on some dense G delta set. If we just intersect all of them, we have that there exists dense G delta set. Let me call it A. Oops. A subset of D sub N, such that Fn restricted to A is continuous for all N. Okay, now by the theorem from the last time, we know that A has this specific form. So we can fix I of N, S of N, so that A includes the set which is obtained as intersection over all M, union N greater or equal than M of I of N, S of N. Okay, and these I of N's are all pairwise disjoint as in the theorem. Okay, so now what do we do next? Well, you see, one nice feature of this sequence is that if you go to a subsequence, but by this sequence, I mean this sequence, sequence of these basic open sets. If you go to an infinite subsequence, it still has the same property. Why is that so? Well, oh, okay, so it's not obvious from here, but it is obvious from what we proved last time. So or is it obvious? No, it is obvious. Yes, sure. Okay, right. So basically, if you go to a subsequence, it still has the same property. So go to subsequence, so that the set X, and here is our set X, N minus the union of all the INs is infinite. Right, we can do that. These are finite intervals. Just take the even numbered ones. And finally, let's see. So what were the names of these things? So there is B in D and restricted to X. So let B in D sub n restricted to X. Note, by the way, n minus x, I think I said restrict, I was thinking n minus x. N minus x is the union of these intervals. So B is just the sum of these S of n's for n in n. I'm putting sum under quotation marks, so it's really concatenation of all the S of n's, right? And now, then, if you look at a function that sends d sub x into space y, I think it was called y, defined by a, goes to fn of a plus b, what do we have? Well, a plus b, so let me just say, so this is continuous for all n, because a plus b belongs to this set A. Right? A plus b has the property that when I restrict it to interval I sub n, for infinitely many n's, I get exactly S of n. So this element falls there, and that's what we were supposed to prove, right? So this is Gn. Okay, now just to give you some idea of what is going on, these sets dx are going to occur in our proof as sorts of discretizations of those subspaces d sub e. And we'll see that really all that matters is what automorphism does on one of those discretizations. All right, no questions? No. So we are back to our proof that OCA implies every automorphism of the Calkin algebra is inner. And we are basically jumping into the middle of the remaining part of the proof because it seems to me that it justifies better what happens before and what happens after. So let's go. All right. So here is the setup. So we fix a separable Hilbert space H, and we fix orthonormal basis Cn for n natural number. We also fix an automorphism phi of the Calkin algebra, and we fix a lifting which has all those desirable properties that we assured last time. So it sends projections to projections, and it is a contraction. Here is notation that it will be using for quite a while. So if you remember one thing from today's class, remember this notation. It will be used all the time. So if we fix E in part n, and E is going to be fixed for quite a while, and if you take X subset of natural numbers, then look at the following, PEX. So what is PEX? Well, look here what happens. We take n in X and take the span of those CIs for I in En. Now, span of CIs for I in En, it is a finite subspace because En is a finite set. So I'm just taking, let me just think of it this way. Our space X is really a big sum of, okay, not very good with planning space. So let me write it here. So H is direct L2 sum of the spaces span of Ci for I in En. Except that I shouldn't have written L2 here, I should have probably written I. So I goes from 0 to infinity, and here I'll indicate this is direct L2 sum. Right, so what we have here is what Banach space people like to call finite dimensional decomposition. Right, so we have an infinite dimensional Hilbert space, but it's decomposed into finite dimensional subspaces. and PEX is projection to some subfamily of those finite subspaces. Right, so that is a projection, and QEX is the image of PEX under our lifting, and we are sure that this is projection as well. And now remember DE, this is the space, the algebra, actually it's fundamental algebra of those block diagonal operators that respect E. D sub XE is compression of DE, the corner of DE corresponding to its projection. So we are just taking those blocks whose indices fall in X and throwing out all those other blocks. So DXE also looks like DE space, but it is a subalgebra. It's not unital subalgebra B of H. Its unit is PEX. Right, so PEX is the unit of this. Okay, and so again, you see PEXs are all commuting. They form a Boolean subalgebra of projections. QEXs, we have no idea. Right, so we just assure that they are projections, and because phi star is a lifting of star homomorphism, they're commuting modulo compacts, but they're probably not commuting. And we'll have to work hard to assure that we can replace them with some nicer, more regular projections. All right, so the next definition. Let A of n be D sub singleton n of E. Now, what is that really? So it's really those operators whose both range and source are included in this finite dimensional subspace. So if E has, I don't know, 10 points, A of, actually not E, if En has 10 elements, then A of n is isomorphic to 10 by 10 matrices. Right, so this is exactly the operators which send that finite dimensional space to itself. So so An is isomorphic to some m by m matrices, and m is exactly the cardinality of E sub n. Now, what is special about matrix algebras or finite dimensional C-star algebras, where their unit ball is compact in the norm topology, which means that we can choose a finite subspace which is as dense in it as we want. So when I say 2 to minus n dense, what I mean is that if I take any element of the unit ball, if this is unit ball of A of n, then for any point, what are points called? For any point x, there is going to be some element of D of n, which is at distance less than 2 to minus n from that x. And so this is what it means to be 2 to minus n dense. And also you want two more properties of this Dn. We want 0 and 1 to be to be elements of Dn, right? 0 and 1 as operators. And this is slight abuse of language, right? So it's really 0 of that matrix algebra and the unit of that matrix algebra. But you know what I mean, right? So you don't want too many subscripts and superscripts. And also here, U of An is the unitary group of An. Right, so it's a unitary group of m by m matrices. We want D of n to also be 2 to minus n dense in the unitaries. Now, this is not automatic. You can choose a dense subset that doesn't contain a single unitary and doesn't contain 0 or 1. For other different reasons, we'll need all three of these, 0 and 1 and sufficiently many unitaries. All right, so at this point, we have our sequence Dn of finite sets. And that's exactly what we spent a little bit of time studying. So we are now working towards discretizing restriction of phi to this subspace. And now for an infinite x subset of n, Okay, so actually before infinite subset of n, d of e is product of these dn's. Now this is exactly kind of space that we spent a little bit of time studying. Right? This is a product of finite spaces. And dx of e is exactly corresponds to this notation that we had a moment ago. So it is product of those d of m's whose indices belong to x. And now here again, dx of e is naturally a quotient of d of e, but for us, even more naturally, it is a subspace of d of e. Right? We identify dx of e with a subset of d of e by just padding up with zeros. Right? So really elements of all of these spaces are identified with operators in the unit ball of d of e, script d of e. Okay, so some terminology. D of e is a discretization of d of e, and dx of e is a discretization of dx of e. You see, a discretization, there are uncountably many ways to choose a discretization, and we'll have to check that it doesn't really matter which discretizations we settle for. And a little bit more of terminology. If we have A, which is element of D, now this is something, so D is D of E, dx is dx of e. As I said, we'll actually have e fixed for most of the time. And since it's fixed, I'll most of the time not bother to write it down. So it's understood. I mean, unless specified otherwise, it is the e that has been fixed. So anyway, for a in D, support of a is set of those n such that a of n is not 0. And we identify dx of e with those a and d of e who support the subset of x. Right. So so this is what I said before. And now we'll need a little bit of descriptive set theory. Okay, before I read this lemma, just recall that weak operator topology on the unit ball of B of H is compact. And in our case, because H is separable, it is metrizable. This is basically Banach-Haloglu theorem, plus the fact that weak operator topology on B of H is the dual space topology. B of H is the dual of trace class operators, but actually you can just check it by bare hands. It is a nice exercise if you don't know this, of course. Otherwise, it's silly to check that this is really compact and metrizable. And now, because of that, you see, if you look at D of E, no, this is not script D of E. So I hope that my handwriting is suggestive enough. This is Latin, so this is discretization. As a subset of B of H, with its natural product metric topology, it is actually a subspace of B of H with respect to weak operator topology. Not a closed subspace for sure, is a subspace, namely its topology agrees with WOT for weak operator topology. So this is again an exercise. So basically we have this compact metric space sitting there, and the lemma refers to that. So in this relation, we are fixing some epsilon greater than 0, or greater or equal than 0. Actually, we need the case when epsilon is equal to 0. and K stands for compact operators. So this relation equal up to epsilon modulo compacts is defined by saying that X and Y are equal modulo compacts up to epsilon if the norm of the image of X minus Y in Calkin algebra less or equal than is less or equal than epsilon. So that relation is Borel in the weak operator topology. So let's prove it. You see, weak operator topology differs from norm topology, but there is one similarity. So actually, okay, before I say similarity, let me just say something else. So fix Rn for n in n, which is approximate unit of the compacts consisting of projections. Then, oops, my slides disappeared. This is funny. I have never seen this. Oh, I see search. Sorry, I'm experiencing technical problems here with the app. Oh, I see. Okay, right. I was here. Okay. Right. So we have approximate unit of K of H consisting of projections. So then, what is norm of P of X? Well, it is limits as n goes to infinity of the norm of 1 minus Rn x. But by the way, being trained as a logician, I'm always annoyed by the fact that you just write norm and assume that reader can guess what are you talking about. So on the left, we have norm in the Calkin algebra, which is obvious because we have P. On the right, we have norm in B of H. I would rather add some subscripts there, but I'm just following the conventions. And not just limit, this is a decreasing sequence, so this is equal to infimum over all n of norm of 1 minus Rn x. And of course, there was no reason to put to multiply on the left. On the right would work, on both sides would work. So okay, so this is one thing. Now, second thing is the fact that set of all x such that norm of x is greater than some r is fixed. This is open weak operator topology. This is basically the whole point. Why is that so? Well, in order to know that norm of x is greater than r, you just need to fix two vectors basically, and just know what is xc dot eta for well-chosen c and eta. So it's open, and because of that, set of all x such that norm of x is less or equal than r is closed. Again. Right, so topologies are different, but at least this much agrees. This much they agree. And from here, it follows. So what does it mean that norm of P of x minus y is less or equal than epsilon? Well, this is true if and only if. Actually, you know what? I have no idea why I chose less or equal than epsilon. I'll prove it for less than epsilon. It's going to be easier. And then, of course, it's the same. So if and only if there exists M such that the norm of 1 minus Rm x minus y is less than epsilon, right? Basically, at some point, But by this here, if it drops below epsilon, then this is it. And now, what about this set here? Well, this set is not open, but it is at least Borel, right? So it's this is Borel. More precisely, it is F sigma. So it's union. You can look at epsilon minus 1 over n and say less or equal, but we don't need to bar. I mean, Borel is good enough. And there exists M, so it's countable union of Borel sets. And therefore, this is Borel. And of course, this less or equal than epsilon if and only if for every delta greater than 0, norm of px minus y is less than epsilon plus delta. And again, you can just do this with countably many deltas. So overall, the set is Borel. It's actually better than that. I think it's F sigma delta or something like that, but we don't care. We just need to know that it is Borel. Okay. So here we come closer to what we are actually doing. A function theta from dxe into bh, less the unit ball of bh, is an epsilon approximation of phi. So phi is our fixed automorphism of the Kalkin algebra for the next couple of weeks. So it's epsilon approximation of phi on dx. Remember, dx is really dx of e is tacit. If the following holds, theta of a is equal to mod modulo compacts is equal up to epsilon with phi star of a for every a in dx. Now, just one thing that I should remark here. We are supposed to be doing descriptive set theory, so this is supposed to be all definable. This phi star is horrible. We just chose it using axiom of choice and a couple of lemmas. But note that this relation does not depend on the actual choice of phi star of a, because we are looking at equality modulo compacts, right? So even if I chose some other operator to be, the lift of the image of A, this would have been the same relation, right? So okay, so what is this definition saying? Well, note epsilon is greater or equal to 0. I didn't say that. I'll say it now. So if you look at zero approximation, E is just equivalent to lifting, right? Because if you look at equivalent modulo compacts to 0, it's really equal modulo compacts. So this is a relaxation of being a lifting. And the way that the proof will proceed is by producing better and better approximations in this sense, for epsilon equal to 1 over n for bigger and bigger n, and then somehow putting them together. Actually, putting them together a bit will be done today. That's the easier part. Any questions? I always feel sort of apologetic when I'm doing something that involves lots of definitions. I just feel that giving too many definitions is wrong. You should be doing proofs, but just basically here.
Sorry, Ilijas.
Yes.
I'm missing a bit the definition because you say X is equivalent mod kappa epsilon Y. If this inequality holds, no. If this inequality is Borel.
No. Here, brackets. This relation is Borel.
Okay.
Defined by, right? So this if this, yes. So sorry, you should have asked earlier, because I guess what I was saying up to this point probably didn't make any sense.
Yes.
Right. So is it clear now?
Yes,
right?
yes,
Sorry,
yes,
yes.
yes.
So it's so I was trying to, as I said, I'm too apologetic when it comes to definitions, so I want to squeeze them in lemmas to hide that there are definitions. But basically, we are just defining this relation here, right? So x and y are equal modulo compacts up to epsilon if and only if the obvious thing happens, and this relation is Borel. We'll need this fact later on. Okay. So zero approximation is same as lifting, and already if you have epsilon, no matter how small, epsilon approximation is definitely not a lifting. It is something that is off by epsilon even once you mod out the compacts, but it will do. Okay, so here is lemma. If E is in part N and an endomorphism of Q of H has a C measurable, epsilon approximation on D of E for every epsilon greater than 0. Now, this is a huge assumption. We'll have to work very hard for this, but we'll get there. So again, we have C measurable, right? It makes sense because those approximations, they are sending D of E to D of H less or equal than 1, right? So D of E is compact metric space. This is compact metric space. So everything is happening. This is descriptive set theory. So C measurable epsilon approximation for every epsilon. Then it has a continuous lifting on dy of E for some infinite y subset of N. So at the expense of going to an infinite proper subset, we actually get a continuous lifting. Now, continuous lifting is even stronger than what we defined before as topologically trivial lifting, but it works only on this small slice of calculus algebra. So it's just dy of E. Okay, so let's prove. Oops, this is happening every time I try to do this. Okay, right. Oh no, this was the wrong spot. Are we here? We are here. Here. Okay. So let's prove this. Okay. So let's let Fn be a C measurable 1 over N approximation on D of E, right? For N greater or equal than 1. Okay. So we have here these countably many functions which together tell us where things go, right? So you see basically these functions together give you complete information about where an element should go. Now, since these functions are C measurable, and since the space D of E has this nice product form, we know that we can, at the expense of passing to a subspace to infinite sequence of indices, we can assume that all the Fn's are continuous. So find X subset of N infinite and some B. Oh, sorry, actually, I think I was too fast when I was proving this theorem. Okay, so there is, I should go back. I should go back. Just one thing. I was very sloppy. I should go back here. You see, we have different functions here. Oh, no, that's fine. Yeah, no, there are different functions, but the same B works for all of them. So there is no issue here. Okay, ignore me, just ignore me as much as you can. Right, we are here. Okay, find X subset of N infinite and B. So B belongs to D sub n minus x of E, I'm not writing E, such that the function Gn of A, which is equal to Fn of A plus B, by the way, this is really plus, literally, for A in D sub x is continuous for every n. All right, now it is continuous, but it is not elliptic. But let's not worry about that for a moment. Let Q be, let's see, so we removed this n minus x, and I'll write it here. QEX. Remember, just in case you forgot what is QEX, this is phi star of PEX. And PEX is projection to these indices, to the subspaces whose indices belong to X. Now, this is a projection. And then look at this function. Gn tilde of A defined by QEX Gn of A QEX. I claim this is 1 over n approximation of phi on dx. Why is that so? Well, what is phi of A? I can write it as, okay, now we have a problem with notation, but okay, so let's QEX. I'll put dot to signify that it is, we are mapping it to Calkin algebra of phi of A plus B. Actually, I should put dots on A and B as well. QEX, right? Because phi is a star homomorphism. So A, because A dot is equal to PEX A plus B, I don't even have to multiply it on both sides. One side would suffice, right? So I'm using the fact that phi is a star homomorphism, and therefore modifying this function. So what do I have at this point? I have 1 over n approximation, and it's also continuous because Gn is continuous. I'm just multiplying on both sides by a fixed element, so this is still continuous. So it's approximation and continuous. All right, so I have these countably many continuous functions which on dx work as they are supposed to work. Now let's look at this. Let A be the following set. The set of all pairs of the form A, okay, use that B, let's call it C. A belongs to dx, C belongs to the unit ball of B of H. And what is the property of A and C? Well, C is equivalent modulo compacts up to 1 over n to Gn tilde of A for all n. Right? So I just defined the subset of a square. At one side of the square, I have dx. Here I have B of H. And basically, just think of it this way. So you have these functions, Gn, we have their graphs, and each one of those functions is trying to guess what is the lift. As n increases, their guesses are getting better and better. So the set A is a set of those pairs for which each function guessed correctly what it is. Right? Okay. So then, first, A is Borel. Why is the Borel? Well, this is a Borel relation. This is a continuous function. Okay, so maybe not Borel. No, it is Borel. Just a second. I'm just worried because the image under continuous function of a Borel space is analytic, as we said. So
but aren't you taking the inverse image of that relation under the map that sends AC to C GN tilde of A? So it's Borel.
That's what I would love to be the case, but I don't see why am I taking inverse image, because it's really I'm computing this in the range. Sure, if I'm taking the inverse image, then I'm in good shape, right? Pre-image of Borel set is Borel. That's fine, but I don't see that. If you see that...
well, you're saying C comma GN tilde of A belongs to the relation as an ordered pair, right?
Oh, yes, thank you, of course, thank you. Yes, thanks, Pedro, yes, yeah, thanks. Okay, so... Right, exactly. So yes, so I'm taking pre-image of Borel set, and I'm taking intersection of count Lemma. Thank you so much. So A is a Borel set. Yeah, I just have these blackouts every now and then. Okay, so A is a Borel set. Now, what else do we have? For every little a in the X, if I look at A, comma phi star of A, this belongs to A. Okay, too many A's, but the point here is that this section at little a is non-empty. Why? Well, because phi star of A is lifts A. So this is that, and 3 is that for every C in B of H less or equal than 1, if AC belongs to A, then C minus phi star of A is compact. Because the only way that it can be equal to countably many, to these all of these Gn of A's, to each Gn up to 1 over n mod compact, is that this difference is compact. So basically, what A looks like is exactly the way that we want this thing to look like. So each section is non-empty, and it contains just compact perturbations of a fixed operator, and fixed operator is exactly phi star of A, which we want it to be. Okay, so by Yankov von Neumann, find a function h dx into B of H less or equal than 1, which is C measurable, and the pair A comma H of A belongs to A, for all a in dx. Right, so there is C measurable selection. Now I promised continuous, but we just apply that theorem before the theorem from the last class again, actually from the beginning of this class. So now find y subset of x and some d in n minus y, so that the function that sends a to a plus d, h of a plus d, for a in dy is continuous, then the function that sends a, so we just have to do it once again, a goes to q e sub y, h of a plus d, q e sub y with the appropriate embellishment with dots. No, actually, no, I don't want dots here. Sorry, I don't want dots here. So this function is a continuous lifting of phi on d sub y. All right. So so you see, all that we need to do is find epsilon approximation on each one of these combinatorial spaces. Okay, so here just a reminder, this xi is a capital Xi or xi or he. I've heard all pronunciations. A function xi from D to B of H is of a product type if there are orthogonal projections Rn in B of H and functions Cn from D of n. Remember, D of n was that nth finite product space into Rn, into the corner of B of H corresponding to Rn, such that, and now here I have this infinite series, but it's strongly convergent. Xi of A is sum of Cn of Ans for all A in D. Now, this is a key definition, really. So let's just see what does it look like. Well, you see, our D is really isomorphic to product of some matrix algebras. Oh, actually, no, it's not. No, it's not. These I was going to non-discretized space. So it's product of D of n's. So what we have is function from D of n into this corner Rn B of H Rn. This is Cn. Now, what is important is that these projections Rn are orthogonal, meaning that there is no interaction between images of Cn and Cn plus 1. So really, no, the images of Cn are all orthogonal to one another. So this series makes sense. This is going to be strongly convergent no matter what, because what you have is a sequence of operators of norm 1, which are orthogonal to one another. So the series is strongly convergent. Right, so each dn we map separately, and then this function C just maps the product of all d of n's into really what you can think of as the product of these corners, which is subset of the unit ball of B of H. This is D. So this is Xi, and Xi is just sending each of those factors separately. All right, so our next task is to prove that we can go from where the last lemma left us, from a continuous lift to a lift of product type. Okay, but before that, an easy lemma. So we have basically lemma which just shows that it doesn't matter how we choose our discretization. So E is in part N, and we have D of E and D prime of E, two discretizations of D of E. Right, so we just choose different finite subsets so that the N set is 2 to minus N dense. Then two things. First, there is a continuous function of product type from D of E to D prime of E, such that X minus theta of X is compact for all X. And second, if E is in part of N, actually I don't have to say it again because I already said it before, so I can just delete this. So if phi is an endomorphism of Q of H, then phi has a continuous lifting on some discretization of D of E, if and only if it has a continuous lifting on every discretization of D of E. Right, so choice of discretization doesn't matter. All right, so let's prove. You can see here that the next item is the key lemma, but I don't think we'll make it there today. So we'll just have to prove the easy lemma. So what is function theta? Okay. So proof of one. Well, okay, so we have. Okay, I'll write D for D of E, and I'll write D prime for D prime of E because E is the same throughout, so I don't have to write it all the time. So D is product of the n's. D prime is the product of D prime of n's. Now, how do I define theta n from Dn to D prime of n? Well, basically, whatever you do, it's going to work. Dn and D prime of n are both 2 to minus n dense subsets of a fixed compact metric space. So I just define it so that the distance between theta n of x and x is less than 2 to minus n for all x. Now, I'm just choosing it, but if you want to have a nicer function, just remember these are finite sets, so each one of them has linear ordering. You can just choose the first element which works. If it makes any difference, or there are all sorts of things you can do. So anyway, so we just choose it this way. So then, okay, so theta of sequence xn is just sum of theta n of xn's. Well, what do we have? These elements live in orthogonal blocks, and the operator norm on such orthogonal blocks is the sup norm. So if I take x minus theta of x, if I remove first n blocks, the norm of the difference is going to be sup of 2 to minus k for k greater than n, which is 2 to minus n. So this is a compact operator for every x in D. Right, and this simple proof also shows that really discretization gives you all the information you want, right? Once we have a nice lift on discretization, we can just compose it with pretty much identically defined map on all of D of E. Right, so that was part one. Part two. If phi is an endomorphism, then phi has a continuous lifting on some discretization, if and only if it has a continuous lifting on every discretization. Well, just compose it with theta. So theta, as in 1, is continuous. And you see, this is one useful feature one of many useful features of these product type maps. They're continuous. If you're looking at the product topology on these finite sets, then right. So what happens to a sequence just depends on its initial segment. So it's continuous, and composition is continuous. All right. Any questions? Okay, so that was easy. Now, okay, so now I'm in trouble because I have 15 minutes left, and there is non-trivial lemma, and I'm in bigger trouble because I've misspelled friend's name. So this is not sure. Okay, so I'll basically say a few words about this lemma. Okay, let's go. I haven't been saying much about history here at all, and maybe this is a good moment to say a few things about history. You see, this proof basically goes all the way back to late 70s when Sherlock proved the groundbreaking theorem that I'm not going to state right now, but thanks to Sherlock, we have the entire subject. Later, that subject was picked up by different people. We introduced Boban Veličković, even myself. Here is the key lemma that was in Sherlock's proof. It was basically hidden, but Winfried and Boban sort of brought it out to actually, basically said, okay, so this is what is going on. Once you get a continuous lifting, then you can do this. There is basically a long sequence of lemmas of this sort. This is not even the latest one in the sequence. There are more improved versions due to, Alessandro Vignati, Paul McKenney, Andrea Vaccaro, and so on. Anyway, so here is in our situation. So if E has a continuous lifting theta on D of E for some E, then it has a lifting of product type on dx of E for some infinite x subset of A. Right, so the lemma literally says that you can go from continuous to product type. And this is what happens in all of these situations. And the terminology, method of stabilizers goes back to introduced, who really saw what was going on. All right, so I'll try to sketch the proof. Now, I have to say that this is not my favorite proof. It's kind of intricate. Once you see what's going on, it's clear, but writing it may take a while, and you may end up writing something wrong, which is what happened to me. So I may have pointed out before that there is an errata page for my book on my homepage, and among lemmas whose proofs are kind of messy is this one here. So actually, this proof has been completely rewritten. I think it takes 3 pages there with more details, because idea is obvious, and as Littlewood said, 2 skipped details may end up with giving you an impasse. That's what happened here. Anyway, so it was enough of rambling. So here's what is going on. We are taking advantage of the fact that we are working in these product spaces of finite spaces. So we recursively find an increasing sequence Nj. So here, n of 0 is 0, and this increasing sequence of natural numbers. And Sj belongs to this D sub Nj. Now note, this is an open interval. So, basically, I'm not choosing anything in the element in that finite set which is indexed by any of the Njs. I'm choosing something in between any 2 of them. So Sj belongs to this, and an increasing sequence of finite rank projections. In other words, approximate unit consisting of projections for the compacts. So that for every j, for any pair A and B in D0 up to nj, here we have closed intervals, so whatever comes before, and C and D in whatever comes after. Let me just draw this. So here we have 0, here is n of j. Now here your A and B are sitting here. Now something happens here, we don't know what. Here is n of j plus 1. C and D are sitting here, there, whatever they are. So for any pairs like this, here's what happens. Theta of A plus S of j plus C minus theta of B plus S of j plus C times 1 minus Rj is less or equal to 2 to minus j. Let's just read this carefully and just see the only difference between these two is what happens in A. Basically, what it tells you is that if you take A and B, this is happening up to n of j, and then here I take this S, so S is the same for both of them, and C is also the same, right? So if I apply theta to these two elements, then what happens is modulo some finite rank projection Rj in norm less or equal to 2 to minus j. Now this is what has to happen because theta is supposed to be a lifting of star homomorphism into the compacts. So you know, the entire idea is that if x and y are equal modulo compacts, then theta of x and theta of y are also equal modulo compacts. So that's what part 1 says. Part 2 is just a mirror image of that one. These are not self-adjoint, so we just have to say it explicitly. And parts 3 and 4 are saying analogous, but much easier to prove thing. You see here differences in what happens after. So here we are fixing A and not B, just A, just what happens up to the njth point, and then choosing two different things. And now we are multiplying by Rj. So we are just saying that once we freeze this part up to nj plus 1, then whatever we put later, it's not going to change what comes earlier much. And this one is also just a mirror image. You see, parts 3 and 4 are very easy consequences of the continuity of theta. Basically, function being continuous means that you can freeze some finite segment and decide what is going on up to any given epsilon. Some work is required to assure 1 and 2. It is pretty much the same work for 1 and 2. So I'll just say, as I said, this is kind of proof that you don't want to watch somebody do it in public, and even less so you want to do it in public. Basically, I'll just wave my hands about the proof, and if you want to look for details, look at the errata of the book, and it is there. So you basically assume that you have chosen n of j for j less than k, and that you have chosen s of j for j less than k as well, and also rj for j less than k. I don't know why I'm writing j less than k 3 times. And now you assume that one fails. Now, what does that mean? Well, it means that you see here is n of j. It means that no matter how you, actually this is n of k, we came, right, j is less or equal than k. That's why I wanted to write it more than one time. J's and rj's are chosen only up to k minus 1, but n of k we know. What that means is that no matter how you choose s here, and no matter how you choose rk, I'll call it rk prime, that there is going to be some pair as and bs such that if I put this S and if I continue it by something, like some C prime, this will not work. Right, so this norm is going to be greater than 2 minus j. And then, okay, so it's okay, so this didn't work. Well, how do you try to fix it? Well, what is important is that you fix this first S and then continue it by something else and try again. And also increase this projection RK prime. So you have some RK double prime, greater projection. But then this fails again. Oh yes, and this other guy failed for some different choice of A and B. Right, it just fails for something. And then it's okay, so fine. So it failed again. Let me try to extend it once again. And let's try to increase the projection once again. Again, it's going to fail for new pair of A and B. You just keep on extending it in this way and it keeps on failing. Now I claim that it has to stop at some point. Assume not. Assume this keeps on failing for infinitely many times. Well, this is again a place where you take advantage of the fact that these are finite spaces. Right? So here we have product of finite many spaces. So certain pair AB occurred infinitely many times. And we kept on extending this S infinitely often. So if you take that pair, AB that repeated infinitely many times, and add this S to them, then theta of A plus S and theta of B plus S, these would have to be equal modulo compacts because theta is a lift. But we were increasing these projections ad infinitum, and the difference was always greater than 2 minus j. So conclusion is that these are not equivalent mod compacts up to 2 minus j, and that's a contradiction. And therefore, at some stage, after some number of attempts, we came to S, which was good enough, which worked for this. So we just stopped there. And then that takes care of 1. To take care of 2, well, good thing to notice is that if you extend S and if you increase the projection, you're not going to spoil 1. Right? So you can take care of 2 in exactly the same way, just by increasing, and at some point the process has to fail. So this is actually one good thing about the proof is that you just keep on trying and you know that you'll get it right eventually, unlike in so many other places. Okay, so that takes care of 1 and 2, and as I said, to take care of 3 and 4, it's really just continuity. You just need to assure that the continuity in weak operator topology. So this is weak operator topology that's just below this projection R, you will not have bigger permutations. Now, okay, so I'm not quite done with the proof, but I'm done with the time. Once you do this, then you just need to chop up this function and use these stabilizers. So this, they call it anything? Essentially, we'll just take X to be the set of all n of j. Remember, we left j's intact. We didn't do anything with j's. So X is set of all n of j for j in n. And what is function? It sends A, which belongs to dx, to theta of A plus sum of all those sj's. This is not quite of product type, but the errors are small and you can truncate them. So yeah, so I should finish here. I suggest that you take a look at the proof. I can say a few more words about the proof next time, but this is probably a good moment to stop this. Let me know if you have any questions. Okay, looks like a no. All right, so take care, be careful, and I'll see you on Friday.